to get started. I wanted to follow up on a topic that we touched on yesterday. I mentioned this Gutowski plot. It has to do with with environmentally friendly processing and manufacturing and sustainability. I have two versions of the Gutowski plot here. I thought we could talk about that before we jump into to mechanical properties in DED. So what this plot shows, and I think we touch on it again in a later lecture, but this shows each dot represents, each symbol represents a manufacturing process. And what Gutowski has observed is that the amount of energy that's required to complete that manufacturing process depends on how fast we can create parts using the process. So what's shown here is this is in joules per kilogram, energy per unit mass, and the x-axis is the build rate, so many kilograms of material per hour. And what we see is that there's a reasonable correlation, and it's inverse, so that the faster we build, the lower the energy requirement to do that. And if we concentrate on additive manufacturing, let's see here. I think I can do this. Let me look at the other. I think this shows the additive processes. So what we see here, I sort of zeroed in on those processes. Material extrusion, the so-called BAM process, was developed in Tennessee. It's a big area additive manufacturing. It's just massive deposition of polymer to create large structures. And it has a very high build rate. You can see here, we're talking 10 kilograms per hour being deposited. But coming in up on that, we have, there's, DED shows up here. There's one data point, but obviously there's a widespread in the build rate across directed energy deposition. And so certainly this is, down at 0.01, 0.02. So we're talking 10 or 20 grams per hour. Clearly the electron beam wire processes clearly would build, certainly could easily do 1 kilogram an hour. And so what it does is it drives us down the curve. So the processes that create a lot of material, that deposit a lot of material very quickly, not only have the advantage of making big parts, but they're also environmentally friendly. I guess that's the bottom line here. So let's see, I think somewhere back here is okay, I think we're ready to go. So I'm ready to talk about service or mechanical properties of directed energy density parts. And certainly with metal processing, the parts generally, almost all of the parts created are intended to go into service. We have a few metal parts that are used as prototypes or as test parts, but generally these are parts that go into service, or they're designed to go into service. Okay, here we go. So there in general, there are really three approaches to doing metal part production within additive manufacturing, and they're actually the three processes that we talked about yesterday in looking at the 1998 roadmap study, where we have basically direct metal machines, indirect metal machines, and then conversion technologies. So the first of these would be direct approaches. This certainly would be where directed energy deposition would fall. In this case, we simply use a fusion approach to melt the feedstock and to form the part directly. So what comes out of the machine is, it would be, the metal part, maybe a little bit of post-processing to do, for example, to remove support structures and to cut the part away from the base plate. But in generally, basically, the part comes out of the machine, more or less ready to go. Maybe some heat treatment, but fairly simple secondary steps. The second approach are these indirect binder approaches. I mentioned Desktop Metal, X1 do this approach where they take where they use the binder jetting approach to create a part that's polymer bound, and then do a significant amount of post-processing to burn away the binder and to powder center the part to create the metal part here. So that's again is a secondary approach. The advantage of this approach over this is really in machine cost, because here we're simply spraying binder down at a very low temperature, room temperature, to create, and so the energy requirements are much smaller than what we have here, and the machines are much cheaper. So then the third one are what I mentioned was conversion technologies, where effectively we build a part that would be like this part. It looks like a nylon part or maybe a polypropylene part, where the part is built in the wrong material, but then this material, this part is used typically to create a mold, but there are other approaches as well. But typically we create a mold cavity with this part and then do a regular casting operation to create the metal. So these are generally the three ways that we get to metals. There's been an evolution over the years. We started off with a lot of this and a lot of this. I think nowadays we see a lot of this, just because we get the part out quickly and more or less ready to go. Okay, so I think, let's see, so here are usage for, and it's the same kind of table, except it lists specific materials, and it breaks down the 7 processes a little bit. So, for example, the first of these is for laser powder bed fusion. I think it may be too fine print for you to see. Then comes electron beam powder bed. Then this one here, which is very complete, is the laser-based DED. And so being very versatile relative to the metals that can be processed. And this came out of a material handbook. It's an ASM product, volume 24A. Volume 24 and volume 24A are two compendia that deal with additive manufacturing. And they're quite nice
resources. But anyway, what we see is that there are a number of nickel-based alloys, a number of iron-based, some copper-based alloys as well. And this table goes on multiple pages. I think I have maybe the second page here. Yes, here's part 2. Cobalt-based materials, titanium-based, aluminum, and the refractory materials. And again, we see that that the preponderance of materials can be done at least with laser-based DED. Here's the electron beam DED here. And so we have parts that can be materials that can be processed with that as well. And this is the arc DED. And again, there are a number of materials that can be processed with that technology as well. So again, I think it's a useful source for being able to understand what metals can be processed by DED. Okay. Typically, I show here the typical mechanical properties that engineers are interested in for applications, and I list them in a particular order. And it's the properties are the stiffness, like the Young's modulus, the strength, hardness, ductility, toughness, and fatigue, the cyclic fatigue properties. And it turns out that in general there's a broad trend if we compare metals, say a forging made by traditional forming with an additive manufactured part of the same composition. But what we find is, and this is very predictable, how the mechanical properties relate based on the manufacturing process, and that is the stiffness is if we compare a forging to an additive manufactured part, the stiffness is typically almost identical, and certainly for high density parts. And let's assume that these are high density parts, the stiffness is virtually identical. The strength and hardness go together, and the additive manufactured parts, at least coming out of the machine, are almost universally stronger than the traditionally manufactured counterpart. And the reason that's generally given is that with additive manufacturing, the cooling rate is fairly high compared to, say, a forging or a casting, and what it results in is a finer structure, and we get basically sort of a pitch-style strengthening effect. I always say that, and I always follow up by saying that people that actually do the calculations based on the pitch equation is that the strengthening is greater than what pitch would predict. So there's still something going on. Maybe there may be an increased dislocation density, perhaps, as well from the high cooling rate. The statistically necessary dislocations perhaps are higher as well. But at any rate, regardless of the mechanism, the parts that are produced by additive are stronger and harder, since they hardness and strength kind of measure the same thing. I've sat in, perhaps you have as well, I've sat on many talks, and I've actually done it myself on multiple occasions, where in talking about the mechanical properties of additive manufactured parts, what we do is we do a simple tension test. We measure the yield strength and the tensile strength, and it shows up as being excellent compared to handbook values made by traditional manufacturing. And we sort of declare victory and say, look, we've done it. Well, it turns out that's really not the case, because it turns out that this list of mechanical properties is in a specific order, and the order is based on how sensitive the property is to defects, like porosity or oxides or other things that can kind of creep in with additive manufacturing. So it turns out that the strength and the stiffness and the hardness are relatively insensitive to porosity, say, for example, or other defects. The ductility is, once we get to the ductility, it's a different story. Because the ductility, as well as the so-called dynamic properties, the toughness and the fatigue, are increasingly sensitive to defects. And the fatigue is extremely sensitive to defects. So what we find is really, if you really want to declare victory in terms of mechanical properties for additive, you really should be down here doing toughness and fatigue tests, because if you can get these parameters to match the forging or the casting, then you've really accomplished something. This is really not very impressive to hit strength. So anyway, so this is basically what we see in the slides I'm going to be showing subsequently. It's going to show this. We'll be coming back to this time and time again, and it will be very predictable. Everything is understandable based on the effect of defects on the mechanical property. And then, of course, I have a little footnote here that post-processing to remove the porosity, like hot isostatic pressing or even traditional sintering, in some cases, can restore properties if the interfaces are properly disrupted. So, I can have two particles, if they come together and don't really form a very good interface, we can have interfacial weakness. That's not so much a big deal with metals as it is with polymers, but certainly if we remove the porosity, we improve the parts. And as the porosity goes down, these values all improve. The parameters all improve. So, and again, we're really at a stage today with metal additive manufacturing where if one can work in sort of a best practice mode, we can actually produce really almost all of these properties in reasonable values compared to traditional manufacturing. So that's the trick, though, is using the best practice, because it's easier said than done. All right, let's look at this. This shows a good example of this distinction between the strength and the ductility in additive manufactured parts. It's applied. This is for it's work that Alison Beastie. She's at Penn State University. She did this work in titanium 6-4 about 10 years ago, and it's these are basically DED and powder bed fusion as deposited and heat treated parts. And what's plotted here is the tensile strength versus the ductility of the material. And what we see, the first impression is that there's not a lot of variation in strength. However, there's an enormous variation in ductility. And again, this is indicative of the fact that if we have defect structures, we can get very unpredictable properties. So maybe we have one build that has a higher density than another build, and so we get, from a strength perspective, that it really has no effect, and so we see this relatively tight strength band, but the ductility is extremely sensitive, and so we get these very wide measures of ductility. And so, of course, sort of the classic extreme are the little period dots. I mean, it's not DED, it's the post-treated powder bed fusion. But at a strength level of about 1,000 megapascal, we have ductilities that are as low as 2% and as high as almost 20%. So, and indeed, the historic problem or obstacle to widespread adoption of additive manufacturing has been this. It's not that we can't hit a certain property, it's that we can't hit that property consistently day in and day out with high confidence. And so even, DED also suffers from this issue. For example, if we look at, say, the post-process or even the acid deposit or post-process materials, that's the little excess. So we see there's some excess here. There's also an X way the heck out here. So it's not as bad as powder bed, but it still is a very wide range of ductility for a given strength level. Okay. The fatigue properties are even worse, again, by virtue of the fact that the properties of fatigue are even much more sensitive to the defect structures than is the ductility or the elongation. So what we see here, these are fatigue plots. It's a standard stress amplitude versus cycles per failure plot. It's plotted on a logarithmic basis, so it doesn't have the traditional look. These are just straight lines with negative slopes on the log plot. And this is, again, this came from Lee in 2016. It's all titanium 6-4. In this case, it's all laser powder bed, but we'll get to see the same thing in DED. And it's with and without heat treatment. And he accumulated the results from a ton of investigators. And what we see is it's what I call spaghetti on a wall plot, where it's just the whole graph is just completely covered with data points, which typically doesn't have much value, but we can glean some things from this. First of all, again, I think probably the fine print is too small for you to read, but this black dotted line here and these two lines are actually for conventionally processed wrought material. They're down here, wrought annealed and wrought aged, and in some cases machine finished. So it's basically the best you can do with titanium, and so that establishes a baseline. And you can see though there's quite a few results that are up here that are sort of banging on the door of the raw material. So we've been able to, a number of investigators have been able to produce parts that have outstanding fatigue properties, even coming out of an additive manufacturing machine. And again, some of these were heat treated, some were hot isostatic pressed, which typically will restore all the properties. Then there's some that sort of fail down here, where the properties are not so good. And these typically are as-produced parts that have a fairly high defect. So one of the goals for adoption of this technology is to be able to basically move these parts up here into this band. And again, that's also easier said than done. These types of plots, this was 2016. I can show you plots from the mid-1990s that basically show the same kind of information. If we do the best we can match properties with traditional manufacturing, but otherwise we typically have trouble. So let's look at some microstructures and some values. In high cycle fatigue, this is directed energy deposition plots. It's a plot of the strain amplitude and a constant strain amplitude fatigue test versus the number of cycles to failure. So again, this is sort of the traditional SN curve for in this case it's Inconel 718, a process that's tested at room temperature, which is the triangles, and then also at 650 degrees centigrade, are the red dots. And what we see is that there's a good amount of secondary cracking, particularly at the elevated temperature. I mean, this shows, not very convincingly, I think, a plot where we hored in on the surface where the fatigue cracks were initiated. And what they show here, again, it's difficult to see on the slide, but there are secondary cracks that have opened up in the process, which has again, they speculate that they come from precipitates at high temperature that produce this. But again, we're the fatigue properties, again, the defect structure really has a big effect. So, well, we can, here, this is another case of high cycle fatigue. It shows 3 different processes. SLM, the last one here, again, these are all straight amplitude cycles to failure, so they're akin to an SN curve, but with the straight amplitude listed instead of the stress amplitude. And what we see is the 3 plots. This is powder bed fusion. This is directed energy deposition with a laser, and directed energy deposition with an electron beam. And it's kind of hard. It's kind of hard to compare these since they're on different plots, and they also, it turns out, they have different axes, so it makes it really difficult. But one way to look at this, basically, the point I'm going to make is that the best fatigue properties are actually the lens material. And again, I'm not sure why why she put this little hump here, because the data don't seem to really reflect that. I think we could just draw a regular curve through these. I don't put much value on her little inflection there. But anyway, the point that I want to make is that the best fatigue property comes from the laser-based DED. The worst is from electron beam, and then the powder bed fusion falls in between. And if, for example, if we look, let's say we pick a number here. Let's say we pick, say, 10 to the 4th cycles. So sort of 10 to the 4th cycles, the data is coming in about right here, which comes over to about 0.06. At 10 to the 4th cycles here, we're up at maybe 0.07, and here at 10 to the 4th cycles, we're down at 0.04. So I guess if we want to generalize this, we could say that with DED, that one of the advantages of the laser-based processes is that the dynamic properties, in this case, namely the fatigue properties, are improved. What's shown here, I'm not sure if these curves are familiar to you. I call them Pear-Sertigan plots. Again, it's fatigue data, but what it shows is it's a plot of we're cyclically loading the part, and with every cycle, the crack gets a little bit larger. And so the plot, the y-axis here, DCDN, is basically for each cycle is how far the crack moves in one cycle. And so, and that's versus delta K on the x-axis, which is basically a change in the stress intensity factor, which, if you want to, you can sort of think of it as a change in stress. But what we do is we're cycling, as I cycle up in tension, I'm increasing the stress level, which increases the stress intensity factor. And then when I go to the low end of the cycle, the stress or the stress intensity factor drops. And what I do is I measure that difference becomes, the difference becomes delta K. And so as the crack grows, I could be doing a constant stress amplitude test, so the change in stress doesn't change. I'm loading from 0 to 20 megapascal, for example, and they will be that way all the way through the test. However, as the crack grows, the stress intensity factor will increase. And again, the stress intensity factor is basically, so you think of it as the stress times the square root of the crack size. So the stress stays the same in the cycle, but the crack size gets bigger, and so my stress intensity factor gets bigger. So effectively, as I'm cycling the part during the test, and the crack is growing, on this plot, we start down here at a fairly low stress amplitude, and the crack's not moving very much per cycle. But as the test progresses and the crack grows, we move up this curve, and towards the end, what we have is a very high stress change in stress amplitude, and the crack is growing very, very rapidly in one cycle. And so that's what these plots show. The slope here, and, these are log plots. The slope gives a value of an exponent that's a measure of how resistant the part is to fatigue. And what we want, I guess we want the slope to be low so that it takes a long time to grow the crack. And so having said that long introduction about the Erdogan plots, what we see here is for, this is again for Ti-64, titanium alloy, and the plots are, well, for different R values. So basically these are sort of the same plots, this R equal 0.1 and R equal 0.7. Let's see, I can explain that too. The R value in the cyclic loading, we have a maximum stress and a minimum stress in the cycle. And the R value is the ratio of the minimum stress to the maximum stress. So an R equal 0.1 means basically that I have a very low positive bottom stress and then a respectable maximum stress. For R equal 0.7, over here, if R is equal to 0.7, it means that the minimum and maximum stress are pretty close to each other, right? And what that does is basically the effect of that is it makes, it's basically it's a gentler fatigue test is the way I think of it. So the material can respond better as R gets bigger. And we see that here where the slope of the slope here is less than the slope here at R equal 0.1. This same material, they're both the Ti-64. And what we see here, if you look carefully, let's just look at 0.1, which is it's the more aggressive kind of fatigue test. What we see is that these blue circles, that lie down here, are the conventional, the raw data, right? Everything else is additive manufactured, and so what we see is the effect of this is that it looks like really at every point the additive material has a higher Y value than the conventional material. And what that means is that the additive material has a higher crack growth rate than the material, which is typically not what we like. We would like we'd like this plot to be very low and with a low slope. So we have slow crack growth, and it takes a long time to get the cracks growing. Having said all of that, the main point here is that the additive data is actually fairly close to the raw data, which means again that for a number of for the research that was reported here, we're really doing pretty well in terms of controlling the defects once we get good mechanical properties. So again, the bottom line theme of this lecture is if you use best practice and do a really good job controlling the defects, the porosity particularly, or if you do post-processing to control the porosity, then we can get parts that have mechanical properties that will rival conventionally manufactured parts, say by forging, which would be the case here, or rolling. Okay. There's a reasonable amount of data out there comparing powder bed fusion to directed energy deposition, and I'll start by saying there's really not a big advantage one way or the other here. It's not like one is hands down better than the other. What this shows, this is for data for Hayes 230, I guess the nickel-based alloy that was solutionized in furnace cooled. So it was given the same treatment, but the dotted line is powder bed fusion, and the red line here is for laser-based DED. And this is just a standard engineering stress strain curve from a tension test. And what we see is, I would look at this and say we're pretty much the same in terms of the properties. But if you want to try and split hairs, the laser base, the powder bed fusion part is a little stronger and a little less knuckle than the DED part. And I think, as we will see, if not in this presentation, in a later one when we talk about microstructure, when you look at powder bed fusion versus relative to DED, what we see almost uniformly is that the structure is finer with powder bed fusion. And so again, if we have finer structure, we would expect to see a higher strength. And that's completely consistent with this plot. Okay, we look at another one of these. This shows some data, again, comparing powder bed fusion with laser DED and with rock material, the forged baseline. Again, this is from the same work that Muhammad and others did. It's about 3 years old. And so it's nickel-based alloys get solutionized in furnace cooled. And what we see is that the ultimate tensile strength, I would say, is pretty much equivalent across the board. And again, that's consistent with the fact that strength is typically fairly easy, an easy target to hit with additive manufacturing compared to other processes. So we see that here. The yield strength is down here again. Is I would say it's completely consistent, consistent with the previous plot. The yield strength for the DED material is a little bit lower than the others, but again, I don't put much weight on that because I think statistically that would largely wash out. And then, of course, we have the ductilities as well. So the powder bed fusion, again, I would say these are all pretty much identical as well. So we were able, again, with the nickel-based alloy to hit the mechanicals just fine. Yeah, here's the microstructures I was talking about. This is again for the this is for Econel 718, and it's processed. Each pair here is a different step in the processing and post-processing. And so and not only that, for each pair, the left micrograph is for laser-based powder, powder bed fusion. The right one is laser-based DED. And so we see here this very first slide, the very first pair, this is no heat treatment, so this is straight out of the machine. What we see, you see almost immediately, the striking feature is that the grain size in the powder bed part is lower, finer than in DED. So again, there's no real value judgment here. If you want to concentrate on strength, the powder bed fusion is better. If you want to concentrate on ductility and toughness, the DED is better, right? So you can choose whichever you want. By the way, as you can see from the symbol here, we're looking at the so-called XY plane of the build. So we're sort of looking down the energy being had to see what the microstructure is. That's the view here. So we don't see any of the columnar dendritic type growth in the grain structure because we're actually cutting across that with these views. So again, what we see, just sort of marching through the processing here, the stress relief really doesn't have much effect, and we wouldn't think it would, right? Because the stress relief is primarily designed to move the dislocations around into lower energy configurations. It doesn't really impact the grain size. This is after stress relief and hot pressing, and here we can see there is a dramatic change in grain size. We go to hot press the material. The material sits at high temperature for a long time, so there's plenty of opportunity for grain growth. And we see that both with both powder bed fusion and with directed energy deposition. Although again, starting with larger grains, we sort of end up with larger grains in the DED than with powder bed, but we get coarsening in both cases. Then after the hip, after solutionizing, we have this structure. Again, not much change. And then after aging, we see this. So again, there's not a lot of change in the structure. I think from my perspective, the main takeaway from this is that powder bed fusion compares to DED by having a finer structure, which is going to give higher strength and decrease in ductility. All right, let's we'll look at one or two more, and then we're gonna take a little break in a minute. So let's look at this one. This is a plot again, Eval 718, and we have a number of plots here. Again, it's looking at tensile strength in blue, the yield strength in brown, and the ductility in green. And what we see is this is work from Ahmad. I forget where he's from, but you know, their work is shown here for laser-based powder bed fusion. But they also showed some other research as well, and with some other materials. So basically, this is sort of where we fall with laser powder bed. This is laser DED. This is electron beam powder bed. I guess it'd be like an RCAM process. And then they showed also the wrought values from two different sources. And so what we see, if we really to sort of focus on the laser process DED, which are these two, what we see is, again, I guess from my perspective, I look at this plot and go, it's pretty much the same across the board. You know, one might argue that that one investigator got a lower ductility with DED, but notice the other studies showed this higher value, so I'm assuming that this is sort of in the statistical wash. And that being the case, we're talking sort of ductilities that for the most part fall in, you know, around 15% for the Inconel alloy. Again, you know, that seems to be the case. Let's look at one more here. This is shows the microstructures again from Ahmad, based on, this is Haynes 282, processed the same way. Again, laser powder, laser DED, and the raw material. And again, we can see, I guess one might argue that the tensile strength is a little smaller. I think arguably the yield strength for DED is probably significantly lower than both the wrought and the laser powder bed parts, but the ductilities seem to fall in line at about 30% all the way across the board. So again, I attribute the changes in strength, the red and blue curve bars, I attribute these differences to the fine structure that we get out of laser powder bed compared to a coarser structure in the microstructures with DED. So I think with that, I think probably what we do, let's take a break. We're about halfway through, so I have about a little after 10:40. So why don't we meet at 10:50, 10:55? Let's say 10:53. How's that? That'll give me a 10-minute break. And so let's take 10, and we'll come back and finish this up after that. So let's take a break. Okay. So I think I'm using my voice. You know, I'm getting which sometimes happens, but I hope. Rich marked it down in Pennsylvania. Again, this is Chi 6.4, and with an R of 0.01, which is basically 0, which means that the cycling is from basically no load up to some maximum stress and then back down to 0. So what we see is that, again, it's the maximum stress in the cycle versus the cycles to failure. So again, standard SN curve for fatigue. And what we see on the left side is an optometric lens process, so laser-based directed energy deposition. On the right side is a raw material to compare. So I think it probably would have been a little easier to compare if they were on top of each other. But I think what you can see is the axes are the same scale. And so what we see is that it's basically the same kind of result for the fatigue, that the additive does very well. One might argue that the slope is a little bit higher here than it is here, or the slope is higher here, a larger negative number than it is here. But certainly we start off at pushing 1,000, but sort of this 900, 800 to 1,000 range, and the same is true over here. I should mention the difference between the triangle symbols and the round symbols is whether the samples had a notch in them. So notching the sample obviously degrades the fatigue properties, and we see that here with the triangular parts being a V-notch sample, whereas the circle samples are a semicircular notch, which is less severe. So anyway, so there's that. Recycling powder is an important area. It has impact in terms of sustainability and environmental effects, but it also has a cost effect because the powder is relatively expensive, and if it's not recycled, there's a lot of material loss, and that's costly. So this is work that Matami did in 1922, 3 years ago, to look at the effect of recycling powder on fatigue properties. Again, this is laser-based directed energy deposition, and with Ti-6-4, and R is equal to -1, which means it's basically like a reverse bending kind of test, where the maximum stress is the negative of the minimum stress. So these are probably reverse bending tests that were done here. And what we see is that the virgin powder that has not been recycled shows max stress versus cycles to failure along a curve like this, which is good. But the recycled powder comes in at sort of from a different angle here, generally. Although we see there's a lot of scatter in the recycled data, which again may or may not be a good thing. Typically, it's not. So the other thing that's I think important to show is the number of defects in the virgin material versus the recycled material. There's an enormous difference in the number of defects. There's also an enormous difference between virgin and recycled material in the volume of the defects. So there's a lot more defects, and more than likely they're bigger in the recycled material. And then over here, what we see is this is a plot of the oxygen content for the virgin material versus the recycled material. We see there's a little bit of oxygen pickup, but not much. I would rush on to say that with titanium, oxygen is a parameter that we watch because, for one thing, titanium is kind of a weird metal. Most metals have a very low affinity for oxygen. That is, the metal is exposed to a little bit of oxygen and it forms an oxide compound. That's not the case with titanium. It actually can dissolve substitutionally a very large amount of oxygen in the solid state. And not only that, but as the oxygen goes in, as the oxygen content increases, the ductility and the fracture behavior degrades. So it's important to sort of monitor and watch the oxygen content in these materials. So anyway, what we see is, basically the bottom line here is that the recycled material more defected, had higher oxygen content, and the increase in defects. We don't see that here, but basically it's attributed to what we call satellite formation. What this is basically from the material, the powder that goes into the beam during the laser DED. There are particles that will stick together, but they don't flow into the melt pool. And so we have particles that are stuck in the recycled material. And what that does is it changes the aspect ratio from spherical to something non-spherical, which always has a negative impact on the packing density and other aspects associated with the powder. For comparison purposes, raw titanium with an R with the same R ratio has an endurance stress of about 410 megapascal. And so these are all considerably lower than the endurance stress that we see here. And over here, we're showing endurance stresses, down here around 50 megapascal, whereas the raw material is around 400. So there's quite a difference in the part quality here. I have a few more slides on the mechanicals. This is a fairly complicated slide on the heat treatment properties, the effect on mechanical properties of 316L stainless steel. It's an austenitic stainless steel. It means the iron is in the form of face-heated cubic structure. And this is, again, laser-based directed energy deposition with a whole variety of states. NHT is not heat treated, so this is straight out of the machine. And what we see is, again, the ultimate tensile stress is in sort of orangish brown. The yield strength shows up blue, and the percent elongation is or the gray curves. So the elongation line is over here, and the strength is over here. What we see is that basically the material straight out of the machine, again, shows a high ultimate strength, a high yield, and sort of a respectable elongation. We're talking elongations here, around 80%, which is pretty good. The heat treatments are shown here. Basically, without going into the details, the heat treatments are various combinations of stress relief, stress annealing, and then the 5 and 6 were actually hot isostatic pressed. So that's 5 and 6 is down here. And so, again, what we see is again, across the board, not a lot of change in the mechanical properties. One could argue that the ductility decreases, but the strength is, the yield strength decreases, but the ductility and the ultimate strength stay the same. So the impact of this, of the yield strength going down and the tensile strength staying high and the ductility staying fairly uniform, an impact of that is that the material, as we do the heat treatments over here, the material is becoming more work hardenable, which means that the work hardening exponent is increasing, which typically is a good thing. So we like that for that. But anyway, that's the way stainless works with DED. Here's some examples for aluminum. Aluminum, again, this is ARC manufactured DED compared to die casting, which is sort of like, die casting is like injection molding for metals. You basically have a mold cavity, we squirt liquid metal into it, let it solidify, then separate the die and pull out the part. So it's a traditional manufacturing method. And what we see as we compare ARC DED to the die cast material, which we're talking again, it's aluminum 12 silicon. That's very close to the eutectic temperature for the alloy, which means basically the simple impact of that is that this material is really sort of behaving like a pure metal. It just comes, it's in the molten state at high temperature. It comes down, it hits a temperature, a solidification temperature, and then the melt converts, the liquid converts to solid at that temperature, and then we continue to cool down to the solid state. And that's what happens with this material. And what we see is, again, the ultimate tensile strength is high compared to the traditionally processed material. Again, not surprising, predictable. Same for the yield strength, and the ductility is also actually quite good. I'm not sure what the story is on die-cast aluminum, 12 silicon, but the ductility is only about 1%, whereas in the additive material we have about 4%. I don't really have an explanation for that. effect. So with that, I move to a summary of the mechanical properties for service parts, and this is sort of my takeaway for this lecture so far. One is that in general and additive with metals, we think of three approaches: a direct metal approach, an indirect approach, and a conversion technology. The advantage of the indirect approaches is there's more processing involved, but the machines are typically cheaper. So that's the main difference. Most commercial metal systems have AM versions. Certainly, there's not the breadth that we find in traditional manufacturing, but the important ones have all been ported over. So virtually all of the important commercial metals have an additive manufacturing counterpart, or they're additive manufacturing. And I guess let me also just say, in terms of additive manufacturing in metals, I proposed some years ago, I guess it's been maybe 10 or 12 years ago now, an additive manufacturability manufacturing index. You know, we have weldability, we have castability, we have formability. Why not have an additive manufacturability? And obviously for metals, that parameter would vary depending on the process, but that's the same thing with, say, weldability. Weldability varies across processes too, so there's nothing new there. But at any rate, the one broad general rule for additive manufacturing of metals using direct processes is if it can weld well, it probably can be additive manufactured well. So when we went back and looked at the metal systems that are available for additive, what we would find is that they're all, for the most part, they all have excellent weldability and excellent castability. And that sort of it doesn't really guarantee, but it almost guarantees that we can also process the material using fusion-based additive, whether it's powder bed or directed energy deposition. Okay, so anyway, that's number 2. So we have AM versions. The mechanical properties, I think, can be compared to conventionally processed materials. The differences really are explained, I think, largely on the effect of defects on the mechanical property. I think it's very predictable what we would see. So, for example, I've read a number of papers over the years where they do additive processing, and they talk. They're typically the papers that deal with anisotropy, which is a difference in mechanical property for a given material based on the direction in which I assess that property. So, for example, an additive manufactured part, they'd say do a tension test in the plane and then do a tension test in the build direction. They get largely different values, and they say, well, the material's inherently anisotropic. My response is no, it's not inherently anisotropic. What you have is a poor build. Because if the build is done with high quality, the anisotropy largely disappears. Again, we can find some exceptions to that. That's the general rule, is that the properties that we get out of additive are the same as what you get out of wrought if we control the defect structure. Okay, then finally, AM part properties may meet or exceed those for conventionally processed parts. Again, it's relatively easy to hit a conventionally processed target with the mechanical properties if we control the porosity in the parts. And so that takes care of that. That takes me to the end of this lecture, but what I would like to do, by your leave, is I have a follow-on presentation here, if I can get to it. I think I do. Yeah, what I'd like to do is spend the remaining time talking about a topic that I think is important particularly with directed energy deposition, and that's it's not the future outlook. That's the wrong picture. It's part of orientation. How do we talk about orienting parts in a build? Because that can be important. Let me get my see if I can find my right lecture. Oh, this is part orientation. Maybe I typed up the wrong one. Part orientation. Oh, that's weird. That's not my part orientation. Maybe I won't be doing it. Let's see what this one is. No, that doesn't really work either. Well, I guess maybe if you'll allow me to do this, I was going to do this one at the end, but it seems like I didn't get the part orientation in, and so let me, if I may, switch over and spend 10 to 15 minutes talking about the University of Texas additive activity and the Austin additive manufacturing landscape, just so you can see kind of where we're at with additive manufacturing in the city. And then again, this is just a dozen or so slides. So what I want to talk about is really are three things. First is CAMD, which is the Center for Additive Manufacturing and Design. The Center for Additive Manufacturing Design Institute, I think, which is basically our lab at the university. I want to talk about the Austin additive manufacturing presence because we're sort of a hotbed for additive manufacturing. I wanted to talk about that. I wanted to just say a few words about what I'm up to these days with in my retirement years. So we have the Center for Additive Manufacturing and Design Innovation. There are 10 faculty involved with this center, and we have 2 staff supporting the center. It's about 3,000 square feet of space. There's 4 labs. And you can see that we have the capabilities largely with commercial machines. We also have a good deal of shared resources at the university. So we've got an EOS M280 and a Renishaw additive powder bed fusion machines. We have 3D systems. We have a High-Q, which is an old piece of equipment for doing polymer powder bed work. And then we also have an SLA 5000 and the J750 for doing liquid polymer polymerization. And then we have the usual university support facilities as well. But we have, in addition to the center commercial machines, we have a number of research test beds that for doing a variety of metals in various forms. I think probably the selective laser flash sintering is a technology that we're using laser sintering to sort of bind apart loosely in ceramic, but then using flash sintering is a way to actually very rapidly densify the part. And so it's kind of an exciting topic area. Dizzy Kovar and Joe Beeman at our place we're working on that particular process. So we have the lamps machine is the other one I want to just mention briefly. This is it's a powder bed machine, but it's heavily instrumented so that we can measure all kinds of parameters and monitor things as the parts are being built. And again, that's a powder polymer machine. Then of course we have these commercial industrial machines that I showed you previously. This is the thing that I think is interesting about the what's going on in Austin is there are within the city of Austin. This is a city map of Austin, and the University of Texas, by the way, is right here, and the downtown area is really sort of this area right here. Again, the total population of the metro area is maybe 1.5 million people. But what we have really scattered along the running north and south are about a dozen different additive manufacturing outfits. EOS North America has a very large a demonstration facility in the Austin area, up in North Austin. They're up here. And then you can see there are other activities. They're also in the Temple Belton area, which is, if you see here, there's a major interstate highway that runs through Austin. It's Interstate 35 here. You can see that a lot of the activity, sort of falls near that interstate highway. But if we go up here past Round Rock, probably maybe up in the ceiling somewhere, it's about an hour's drive from downtown Austin. We get Temple Belton, and there are two very large additive facilities there as well. Stratasys has a large parts facility in Belton, and then 14 Advanced Laser Materials is sort of a boutique feedstock supplier. So they'll do formulations of various feedstocks, and they've been in business for 20 years anyway. They were spin up, actually, Advanced Laser Materials up here is they were a spin-off out of my lab. The one commercial success out of my lab with materials development. So again, there's a reasonable critical mass of additive activity in the Austin area that we have. So anyway, I guess just to finish up, I want to say just a little bit about what I'm doing in my post-retirement years. I retired from the university 2.5 years ago, and but I haven't really stopped. I've stopped on my university, but I was already doing a reasonable amount of other activity. There are four activities that I'm really engaged with. One, of course, is the ASDM ISO work. I'm still very engaged with that, with standards development. Again, I was an inaugural member of the committee in 2009. I've been active ever since. And I mentioned to you before, I sit on Joint Group 51, which is about 10 people that are charged with maintaining the additive manufacturing dictionary, ISO ASDM 52900. The second of the four tasks I'm involved with and continue to be is with the Mining Materials and Metals Society, TMS. There may be members of TMS here besides me. It's an international organization, about 13,000 members. And I will, barring a catastrophe, will begin in February, March of next year, a 3-year cycle, the so-called presidential cycle for the society. So I'll serve 1 year as the vice president of the society, 1 year as president, and 1 year as past president of the society. It's a 3-year duty from 26 to 29. I'm pretty excited and looking forward to that. I've also sit on a couple of committees with technical committees in the society, namely the Powder Materials Committee and the Additive Manufacturing Committee. I sit on both committees. There was a time about 4 or 5 years ago where I was actually the chair of both committees. And so I would go to meetings and we would report out on activities. And so I always was able to say it was the AMPM committees that I referred to. So just to get a kick out with the time illusion that we use in the U.S. of AM for morning and PM for afternoon. Anyway, the third activity I'm really involved with is the so-called NCAAS, the Materials Metallurgy Exam Development Committee. I've been involved with this committee for almost pushing 30 years. What the committee is it's a committee that is charged with writing an exam for professional engineering registration. I'm sure India has the same equivalent. You can become registered, right, as a professional engineer. And that typically involves taking and passing a test. And so I sit on the committee that for materials and metallurgy, discipline specific. I sit on the exam committee that actually writes the test for the United States. And so all 50 states use this test. It's given once annually. And I'm very happy to say that it turns out every 6 or 7 years, the committee basically does this massive survey to say what are materials and metallurgy people now practicing engineering in the United States, what are they actually using, and what are the subject areas that they actually work in, as opposed to what were they taught. And so it's a relevance issue, because what we do is we base the exam on what people are actually using. And I'm very happy to say that 2 years ago we did this process, and for the first time additive manufacturing actually appears now on the exam. So, which is great for me, because I can write those questions all day long, right? So, anyways, I'm still involved with that. The last one is it's kind of an interesting area of service. Within the state of Texas, we have, and for high school students, so these are sort of 14 to 18-year-old students before they go to college. Texas has an organization called the UIL. I'm not going to say what it stands for because it's only confusing. But what the UIL does is they sort of organize and legislate and execute competition among high school students across the state. And in Texas, the biggest and most important is in sports. For us, it's American football, because they have an athletics arm, but they also have an academic arm. And within academics, there are so-called STEM contests that are available. And there's the one that deals with it, sort of pre-engineering, is a test that involves using a handheld calculator to solve problems. And since 1982, so now for 43 years, I've been the state director of that test. Again, there's about 3,000 students that take this test annually in the state. And there's a competition, so they start at sort of at a city or a district level, and then the winners will advance to a region. Texas has 4 regions, and then the winners from region will advance to a state meet, which I run every year. We just finished it 2 months ago. And the winners of that become state champions. And there's a lot of recognition. They get medals and other things, and a lot of really good recognition. But I write the exams for the district and regional and state meet. I actually write a total of 10 tests every year. So it's a fun thing to do. It gets me out of the ivory tower of the university, and I get to deal with high school teachers and with high school students, and it's really a lot of fun. So with that, I think what I'd like to do is, we have about 5 minutes left. I thought I'd close with this. I've spoken with a number of you about my wife, Nancy, and turns out that in 2023, 2 years ago, Nancy and I actually celebrated our 50th anniversary, which I understand in India is kind of a big deal, right? But it's also a big deal in the United States. And so you see here we are on our wedding day, 52 years ago, and you see us more in our present habitat. Yeah, so thank you. But she's been it's been a wonderful life with Nancy. She's a wonderful person and a wonderful human being. So we're very happy to celebrate that. And so we're now in the process of growing old together, and we'll see if we're hoping to make it to 60.
Looks like the Titanic couples.
I'm sorry.
Looks like the Titanic couples.
Yeah. Yeah. All right. Yeah. So anyway, so with that, that's the end of that talk. And maybe tomorrow I'll try and remember. I'll make sure and get the part orientation standard description, so that you can see. Basically, there is a standard way to talk about how we orient parts, and for testing, if you want to do a tension test, to specify what the direction of the tension test is, so that I can sit in Austin and explain an experimental procedure that people here in India can understand and work with. So it's very important for communication purposes to be able to talk about how parts are oriented, because again, they can have an impact on the on surface finish, on properties, and other things as well. So with that, I think we could probably stop. I think we're at 11:30. I don't know if you have questions about mechanical properties or anything, I'm happy to address those. But in the meantime, we have a tea break. We start up in 15 minutes with Cosmo. So I guess if you want, if you have questions, why don't you just grab them during the break? I'll be happy to visit with you. And so we're going to go to a break and start up again at 11:45. Is that okay? Yeah. We're good? Okay, great. Thank you.
Participants, any queries? The question is related to mechanical property with respect to post heat treatment. Heat treatment. They mentioned tensile stress elongation percentage around 91. Elongations.
Yeah, that seems weird, doesn't it?
Yeah.
No, anyway, go ahead.
So the question is that acceptable?
The elongations?
Yeah.
Yeah, well, maybe I can find what is, for instance, 91% in metals is unbelievably high.
Yes.
Which makes me think maybe it's not, what they're saying is not what we're thinking. Let me see if I can find what you were talking about. It was one of the elongation ones, right? Yeah, this was pretty reasonable. Yeah, because this includes the necking region, so you get a false measure of what the elongation is, because the sample is thinning down and necking. There's 40%. Sorry? Let's see.
Yes.
This is maybe this one, yeah. Yeah, I looked at this one. Yeah, this one's hard to. It's hard to explain. I can tell you what my best explanation is, having looked at it. I think my best explanation is that they confuse the elongation and the yield strength, and that the elongation is actually the blue, and the yield strength is the gray. That's my speculation of what the issue is here. Because you're not going to see a 90% elongation, even if you include the necking region, I don't think, not in the metal. So my speculation is that the blue is the ductility. That seems to be a little more sensible, perhaps. But at any rate, I think this we really probably will have to discount until we can go back to the paper and see. By the way, but, and if I may do an advertisement at the same time, this paper was published in the SFF Symposium Proceedings in 2022. It turns out that we decided many years ago that the conference proceedings we would put online and make them freely available to anyone. So this paper, during the break we can go online and take a look at it if we have the desire to do so. Because all of the papers for the entire 35 years of the conference are all posted online and available for download, PDFs. So anyway, okay, yeah, thank you. Yeah.
Good morning, Professor.
Yeah.
Again, this is related to the mechanical properties. The comparison of the AM parts to the conventional processes, it's observed that the AM parts have something like stress is increased, hardness is increasing, but fatigue and ductility is found to be dropping little. So do we have to choose about the AM process with the applications, whether if it requires fitting, we should not go for AM parts, AM processing, or if we only require, we strength, your harness is focused, we can go for AM processes. Is that?
Yeah, right. Yeah, I think you're exactly right. The properties, I guess this is really, I guess, true for any manufacturing process where, you know, the properties and the parts service requirements have to match. And again, as you mentioned, I didn't really deal with this much here because I think with directed energy deposition, I think most parts are finished that have high service demands in terms of properties. But it turns out that in general, surface finishing never hurts the mechanical properties. And sometimes it helps. Maybe oftentimes it helps, but not always. I think back, there was some work done by Tom Starr at the University of Kentucky years ago where he did he was doing countervent fusion of metals. And what he found is that there were certain metal systems, namely the ones that have really high toughness, where finishing the surface really had no effect. And the reason was that it was the internal defect structure that was really driving the fracture, not the surface effects. Whereas materials that maybe have a little more, that are less tough, the surface effects can dominate the fracture, in which case, obviously, finishing the part would have a big effect. So we have those balancing playoffs as well. So, but anyway, anyway, your point's well taken.
Again, observing the recycled materials. Recycled materials is finding a good number of defects, attributing to some satellite functions.
Right. Yeah.
So what about it's not additional go to recycling of materials, right?
Yeah, I'm sorry.
The recycling of materials has getting defects,
Yeah.
increase in defects.
Right, yeah, produces, yes, much more effective.
Defects.
Yeah, absolutely.
So what is the alternate or the compensation to improve those defects
Yeah, right.
with the
Yeah, it's a good question. Yeah, it's what I've seen people do with metals. Actually, it turns out I believe there are one or two stamps on dealing with recycled with metals. For certain applications, it's not allowed, so the material must be virgin material. That solves the problem, but it's very expensive. One of the easiest, I think perhaps the easiest solution, at least in part, for satellites, is to take the powder and re-sieve it before putting it back in the machine. So basically, the re-sieving is this classification technique where we take certain size particles and pull them out. We can separate out the coarse particles, which would be almost all of the satellites, from the rest of the powder, and then use that material. Throw away the coarse particles and use the fine particles. And it's a relatively straightforward and inexpensive approach. I don't think it will completely solve the problems, but it certainly would help. Other than that, I'm not really sure what you do for a cheap alternative to get rid of the defective material in a recycling mode. So, let me think if there's another way. Obviously what they do with polymers is they blend. So as a way to save money, they don't throw the powder away, but they'll sieve the powder and then they'll mix it with virgin powder. And so it's sort of a compromise between cost and the performance of the powder. And so, that's fairly typical with polymers like nylon. It's standard operating practice. I would think maybe with metals, it seems like that would be a way to compromise as well. So, yes.
From aerospace applications point of view,
Yeah.
which parameters we have to consider for increasing the mechanical properties or changing the mechanical properties. NFC components, composites, which are ready.
For aerospace.
Yes.
applications, right? Sure.
Natural fiber composites, which are 3D printed for aerospace applications. What should be the considerations in terms of properties or sustainable properties or mechanical properties that it should have?
Right.
What should be the parameters that they have?
Right. Yeah, I'm sure there are fiber composites that that are used in aerospace applications, but I don't know much about them. Unfortunately, what I've seen it's almost exclusively are polymer parts that are used for ductwork and vents. That's really the popular use of additive. When it's completely non-structural, so you don't care about the properties in doing that. That's probably the most popular use of additive in aerospace. But also there are metal parts, right? I talked about the LEAP engine fuel injectors. The General Electric is making, I forget what it is, maybe 15,000 of these injectors a year by additive manufacturing at a facility in Alabama. And they just have a bunch of machines doing nothing but making these parts. But those are metal parts. I'm not sure what the metal is. But as far as composites are concerned, I'm not aware of. It doesn't mean it doesn't exist. I'm just not aware of what's going into aerospace. So I'm not really able to answer the question, unfortunately.